Good morning, folks. This is activity number 2 in lab 11, which is on March 28th, 2023. It's a very simple linear buckling analysis in Catia, and we're going to be comparing it with the Euler buckling formula that is given in the expression up here, depending on the boundary condition that you have at the two ends. This is the stuff that you do, buckling is stuff that you do in your probably third year uh, mechanics classes. And just keep in mind that Euler buckling is a non-conservative value. In other words, the actual physical structure may buckle below, and in fact, well below that buckling load. It gives you an upper bound, but it's not conservative. And the other thing is that the main reason behind the fact that this is non-conservative and it has to be used with a great deal of caution is that it assumes that the structure is perfect. There are no imperfections in it. The load is perfectly aligned with the axis of the beam and stuff like that, which is impossible to do in real life. Now, Katia does linear buckling analysis, and therefore, what happens after the buckling is predicted cannot be done in Katia. In other words, post-buckling, the post-buckling stage cannot be done with Katia. Okay, so here's the situation. We have a clamped beam. So a clamped beam, one end of it is completely fixed, and the other end is subjected to an axial load. And then when that axial load reaches a critical value, which is the critical buckling load, according to Euler's formula, the structure will snap. Okay, now the the nature of the boundary condition, if you look at this chart here, the nature of the boundary condition is right there. In other words, this particular the second one from the right is the situation we're dealing with. One end is clamped, the other one is free. Now, and the value of k, the what is called the shape effective length factor is 2, and therefore in the expression for Euler buckling you have to say k equal to 2, and then you work it out. Okay, the 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 Euler formula predicts a failure of 20 roughly 22,000 pounds. So let's go ahead and make this thing in Catia. We start with a part file. Okay, and on this vertical plane I will sketch a 1 inch by 1 inch, that's the cross section of the beam. 1 inch by 1 inch, so there is 1 inch, there is another one. Incidentally, I'm doing this thing with solid elements. A more appropriate element to use is beam element, which I will not do that in this particular tutorial. I have done it in the class as part of my activities. I'll show it to you, or I've shown it to you, but will not do it in this particular video. Okay, so exit, and then we pad it by 10 inches. So there is my structure. This is made out of steel, so let's apply the material properties for steel, metal, and we go to steel, and on that part we say okay. That's pretty much it. So we're going to go to analysis and simulation, generative structure analysis. I will leave the size the same as it is, although you may want to change it. In fact, this is parabolic, that's fine. You may want a linear or parabolic. Parabolic is more accurate, but I'll leave it the way it is. Okay. Now, let me change the rendering here. Good. This end, I want it to be clamped, or the other end. It makes no difference. Actually, let me make the other end clamped. Okay, this other end is clamped. The first step in doing linear buckling analysis, pretty much in every code, is do a linear static analysis. Notice that when I got in there, it gives me really two options, uh, doing static or doing frequency. Okay, now obviously buckling is not a frequency calculation, but the first step is to do a static case. And what I'm going to do is I'm going to apply a load of 1 pound here. This is a dummy load of 1 pound. And once I do the buckling analysis, that buckling factor, whatever it comes out to be, you have to multiply 1 pound by it to get the buckling load. If I had put, for example, 100 pounds here, no problem. It's just that that buckling factor that you're going to see in the tree later in the uh, selection tab is going to be 100 times smaller than if you had to put a 1 pound there. But oh, you put a 1 pound dummy load here. So that's going to be a load. Where's that force right there on there? And 1 pound. Notice that I already have it in the correct direction. So -1 and 1 pound. Now, by the way, if you do a positive one here, and look at the selection tab, all the buckling factors are negative. That means there will be no buckling with a positive. The tension will be in compression, therefore those factors are going to be negative. But here already put as negative, -1, therefore the buckling factors are going to be, or the scale, multiplier scale is going to be positive. Okay. So we say, okay, so that's pretty much it. Let's go ahead and run it. Nothing exotic is going to happen. It's just going to compress whatever the value is. We don't really care. There we are. So you see, you can see that it compressed. Where's that thing? There. No big deal. Now, now that we are done with this thing, we're going to go and insert a buckling case. See that? Insert buckling case. You click on it. And it says, okay, where is that static analysis that you did? So right here is the static analysis that I did. I have to go and select it. See that? It's asking here for the reference. The reference is the static analysis that I did. And I say, okay, and that's pretty much it. So we have a buckling case here. We had the static case that we did initially, which was needed. Now we need a buckling case, and it asks for where is the static case. We picked it, and now just go ahead and run it. Quick, fast. So if you look at the deformation now, let's turn this thing average ISO. Yeah, good. Let me also hide this element here. Okay, so if you look at the view from the front, from the top, you can see that the structure buckled. This was clamped here, you apply the load, and it has buckled. It didn't just compress. Now, if I double click on this thing, under the selections tab, sorry, under the occurrence tab, I think I kept saying selection, but occurrence tab is what I wanted. Uh, we have a buckling factor. Notice that they come in pairs because this can buckle this way or it can buckle in the other direction. They come in pairs. But this number is not does not match this value. So I wonder what the reason may be. Let's check it out. Uh, the mode shapes are correct, or the buckling shapes are correct, but it is not the value that I got. Let's do the following. Let's go ahead and change the size here and see what happens. Let's say point 2 and run it again. I want to see what is the difference with the buckling load. It's unlikely that it's going to be much different. So there must be something else that we need to look at. Let's check it out. Oh, activate and double click. Yeah, see the number didn't change. So the actual mesh size was irrelevant. There's something else that is going on here. Let's make sure that the material that we're using is actually steel. I thought I used steel, but I'm not 100%. Yeah, steel. That's fine. And the load mode, the applied load was 1 pound. Yep. Let's check it out. 1 pound. That's correct. So something is not working out here. Let's check. Uh, Oh, I found out what the issue is. This is not steel, okay? This is aluminum. That's why these values are different. So actually, it's not surprising because the value of the buckling load that we got is almost three times that because the Young's modulus for steel is almost three times that. Okay, so let's go clean this up. So back to let's go change the material here. Let's go to the let's go to the part. I'm gonna delete this, and apply material, but this time aluminum, metal aluminum on this part. Yeah. So okay. Now we're gonna go to our generative structure analysis and run the buckling case again. By default, the static case is going to be run also. Yep. And now if you deactivate this or activate it and double click on it and select the right there, select the buckling factor, you get 20,000, and that is in agreement with 22,000 here. Now, it really doesn't matter if I chose the original big size element because I made it a lot smaller. I wanted to see effect of size on that. But even if you go here, maybe point 0.8, I think it was 0.6 or 0.7. I'll make it 0.6, okay? And run it again. So it's a much bigger mesh, much coarser mesh. You can see that. Let me change the rendering here. Yeah, much coarser, very coarse mesh. Okay, so let's run it. I don't think it's going to make that much of a difference. You're going to be in the vicinity of that 22,000. Okay, so double click. Yeah, yeah, 20,000, 21,000. Didn't make any difference. Okay, so I made a boo-boo here and used steel instead of aluminum. Obviously, a bad mistake. Uh, so it agrees. The results agree with the Euler buckling. Good luck.